Visibility of detail is an old concept that was first proposed over 20 years ago. It was originally proposed to separate the concept of detail, which has its roots in system geometry, i.e. SID, focal spot size, pixel size, etc., to include non-geometric factors that include contrast and density. For digital radiography, density, which is mainly controlled by MAS, will be presented. Also, the closest concept to visibility of detail we have in today's world is contrast resolution. Before we start our discussion of visibility of detail, there are some definitions we should review. The first is quantum model. Quantum model is the grainy appearance seen on digital radiographs. It is a product of low signal-to-noise ratio. Quantum model is reduced by increasing the amount of radiation reaching the image receptor, which increases the image signal compared to the noise inherent in all electrical circuits. Density saturation is the point where the pixels on the imaging plate reach or approach their maximum value. Pixels that should be dark gray cannot be adequately differentiated from black pixels. Density saturation happens in cases of extreme overexposure. For objects to be visible, they must have a density difference from their surroundings. As this density difference decreases, the ability of the computer to demonstrate small objects decreases. This is where KVP plays a role in digital imaging. High kV techniques will project less contrast onto the imaging plate and therefore may not demonstrate small, low-contrast objects as well as low kV techniques. So the concept of visibility of detail encompasses all the geometric factors that affect detail like motion, SID, OID, focal spot size, pixel size, etc. With the addition of anything that makes small objects difficult to visualize from their surroundings, low contrast, under or overexposure, radiation fog, or quantum model. Below are some extreme examples to make a point. In the block on the left, the word visibility is difficult to separate from the background. It is nearly the same density as the background. In the days of film screen radiography, it might be characterized as overpenetrated. The KVP was set so high that the bone shadow was penetrated by excess radiation. The solution to the problem is to make the text brighter than the background. This is done by decreasing the KVP. Decreasing the KVP increases radiation attenuation in the part, making it stand out relative to the background. The second problem arises when there is fog or excess noise overlaying the object being demonstrated. This is typically caused by poor collimation or neglecting to use a grid. Correcting for the problem reduces the fog, thereby increasing contrast. In the world of digital radiography, there exists a step in image processing that didn't exist in the film screen era. This entails the step of image correction by the computer. Overexposure is difficult to accomplish because the amount of radiation necessary to cause it is so great. A radiographer must overexpose an image by 8 to 16 times to make the image so overexposed the computer can't correct it. The pixels that represent the part imaged are as dark as the background, and the computer can't separate them from the background pixels. I call this amount of overexposure density saturation. The background pixels have reached the highest amount of radiation that they can measure, and the part radiographed is at its maximum as well. To correct the error, a decrease in MAS is recommended. Using too little radiation also causes excess quantum model. and the computer can't separate the white pixels from the very light gray pixels. Correcting this problem is easy because just increasing the MAS by 2 to 4 times will fix it. Here we have 3 images depicting a dorsal plantar projection of the foot. The first image was exposed using 0.125 MAS, the second using 2 MAS, and the third using 32 MAS, all taken using 53 kVp. All 3 images were selected from the series of exposures where I successively doubled or halved the exposure from a reference technique, the center exposure. The overexposed and the underexposed images were selected from the series because they demonstrated conclusively a particular exposure defect. If we compare the first 2 exposures, exposure 1 uses 8 times less radiation than exposure 2, with exposure 2 falling at the bottom of the acceptable LGM range of 1.9. Let's take a closer look at the images. The image on the left is grossly underexposed. Note that the anatomy past the proximal phalanges detail is not visible. This is due to a lack of image information reaching the imaging plate. The computer cannot differentiate image data from noise. This is known as low signal-to-noise ratio. If we zoom in on the images more, it becomes apparent that when viewing the exposed areas not covered by anatomy, quantum model, a grainy appearance, is visible. This problem cannot be corrected by reprocessing, and the view must be repeated by adding radiation to exposure with an increased MAS. Now let's compare the second and third images. The image on the right was overexposed by a factor of 16 times. Note that the distal phalanges are too dark for proper interpretation. Also, this overexposure is so severe that the image cannot be corrected by the computer. The computer cannot differentiate anatomy from the background. The image is density saturated. A simple adjustment of the MAS from 32 to 13 MAS solves the density defect, but doesn't address the patient overexposure problem. An additional problem highlighted by the green borders with this exposure is that the computer was unable to mask the unexposed areas of the exposure. An overabundance of scatter flow caused this problem. Here are 3 images, 2 out of the manufacturer's recommended range of acceptable values, which is an LGM of 1.9 to 2.5. The middle image has an LGM of 1.9. At first glance, the anatomy is equally demonstrated in all 3 images. Magnifying the first 2 images reveals that the 2 times underexposed image demonstrates quantum model. The grainy appearance of quantum model would be more apparent on the radiologist monitor due to its higher resolution, which is most evident in the area just to the right of the foot. Now, let's compare the in-range image with the 4 times overexposed image on the right. Upon close inspection, the overexposed image appears smoother and is an acceptable quality image. This image suffers from 2 problems. 1, the patient received more radiation than was necessary for the view, and 2, the auto-masking software malfunctioned and this image needs to be manually masked before it is submitted to the PACS system. For digital radiography, density is the important factor that must be considered to produce good quality images. Density is primarily controlled by MAS and is affected by body part size or habitus. In the case of overexposure, the patient receives more radiation than is necessary to produce a quality image. In reality, it takes an absurd amount of radiation to reach the point of density saturation, where the computer can't correct the image. Lowering the MAS by a factor of 2 to 4 times or decreasing the KVP by 15 to 30% will fix most overexposure problems. For underexposure, image quality suffers. It will demonstrate excess quantum model. This happens with exposures that are 2 times underexposed or more. Underexposed images may require a repeat image with an increase in KVP or MAS to provide adequate density. To correct visibility of detail problem, you first need to determine if the image suffers from a loss of detail or suffers from a density problem. Contrast is not an issue in normal radiography because if density is properly set, contrast will be corrected by post-processing in the computer. As detail goes up or down, visibility of detail also goes up or down. So it is good to consider adjusting factors that affect detail first. Eliminating motion is a good first step because motion has the greatest effect on detail of any factor listed. Then comes smaller focal spot, reducing the OID or increasing the SID. Note these factors have in common that they are geometric. Contrast for the displayed image is ultimately controlled by the computer's image reconstruction algorithm. You can influence the likelihood that the software will see a small object that has little contrast by lowering the KV or reducing fog by increasing collimation, or with the use of grids, or by blocking excess radiation from reaching the image receptor. Finally, simply increasing the MAS will reduce quantum model on the image, thereby increasing the visibility of detail. Just remember that increasing MAS also increases patient dose as well. So to summarize, the factors that will affect visibility of detail and have no effect on detail are: overexposure is a conundrum. If kept within certain bounds, it can be beneficial to an image. A radiographer has to remember that part of our job is to reduce the patient's exposure to radiation, so careful selection of technical factors and limiting radiation dose is important. Underexposure is more of a problem. It can lead to an excess quantum model and can only be corrected with the repeat exposure. It is adjusted so more radiation reaches the image receptor by increasing the MAS or KVP. As I mentioned earlier, the computer controls contrast in the final image. High KV techniques yield less patient dose, but increase the likelihood the computer will not demonstrate small, low contrast objects, as opposed to low KV techniques which increase the likelihood of imaging small, low contrast objects, as in the case of mammography. Finally, some bad effects of out-of-range techniques may be more visible on your radiologist monitor, but not on your monitor. Radiologist monitors display a higher resolution, so defects like quantum model will be more noticeable and more of a distraction for the radiologist. Thank you for your attention. This will end my presentation.